Okay, so thanks a lot. So I will talk about slab tearing and the origin of SJAM. It's an acronym that we came up with, spatially and geochemically anomalous arc magmas. And as I mentioned in the introduction before, it is the topic of our new ARC discovery project with Mike Sanifold and Teresa Ubide. And it kind of forces me to become a little bit of a volcanologist. I'm a structural geologist, but I started, I was always interested in volcanoes, as you can see here, but actually what I did here, that's in Mount Etna in 1999. And what I'm actually doing is preparing the ashtrays. So just taking bits of lavas and kind of mold them into a shape of an ashtray, putting a coin, and keeping it as a souvenir. But Mount Etna is a classic SJAM volcano. I did not quite appreciate that when I was there 20 years ago. So I'll talk a little bit about Mount Etna and about other examples where magnetism in the proximity of the arcs is not quite in the right place, and it is not, it doesn't have the right geochemistry. So something else is going on there, and very much linked to the kind of processes that Louis has presented there before. So I will talk about a number of things. First of all, slab deformation and arc magnetism. So the relationships between deforming slabs and magnetism, tearing and the magnetism in the northern Andes. So just an example from the Andes that we have published recently, and kind of general spatial and geochemical patterns in modern arcs. So that's the kind of work that we started to do now in more detail, and it's all kind of half-cooked or even less than half. So you will see all sort of diagrams that are yet to be interpreted. And finally, if I have enough time, I'll talk a little bit about the implications to ore formation. We think that it is important because if we look at the ore deposits, they occur in arcs, but they occur in special places. So they are clustered in time and space. And in many examples, we can see that the ore deposits are the exceptions rather than the rules. There are places where something went wrong with the system. So maybe it is the SJAM that has some, that can give us some insights into the formation of ore deposits. Okay, so let's start with a couple of statements. First of all, that subducting oceanic lithosphere must deform in complex ways by bending, stretching, and tearing. So we need to get slab deformation just from the way that plate tectonic work. Again, we saw that very clearly in Louis' presentation. So for example, if we have edges of subduction zones, this is the Caribbean slab, and it has an end, obviously. Yeah? There's an end here in the northernmost part of South America, and the slab edge.
Hello? I'm sorry, the slides are not moving on our Zoom.
You don't see the slides?
No, we only see the first title. So the slides are not moving. Sorry about that.
Yeah. It's because sharing is stopped, so that makes sense.
Oh, okay.
So thank you for letting us know. Okay, how does it look?
Oh, perfect. Thank you very much.
Okay, please let us know if there are more technical problems.
Cool. Sorry for the interruption.
Yeah. So there's an edge to the slab, and obviously something else has to happen. At the edge, there has to be termination of the arc. There has to be some changes there has to be some gap in the lithosphere. A slab window, slab tearing, something like that.
Just use the mouse pad. The same reason.
Oh, let's I lost the. Oh, here it is. Okay, so other examples along the same line. If we have along strike variations in trench migration, yes, the subduction zones are the tape boundaries are mobile. The many subduction zones are retreating. We can get a part of the subduction zone advancing. And if we have along strike variations in the rate of subduction rollback, then obviously the slab needs to be stretched or subjected to tearing. So an example here from the central Mediterranean, we see a kind of tectonic reconstruction of a subduction system that migrated eastward from say 5 million years ago to present about 600 kilometers. And in the course of that migration, the central part is the part that migrated most. And obviously the slab needs to deform. Yeah, it can stretch and it can tear. So that's the other example. And again, I lost this animation. I hope that will not be the problem in all the presentation because it will be a bit annoying. And the third example is the transition to flat slabs. So we see the Mexico flat slab, for example. Here we can see the contours of the slab depth. And again, if we move along strike, from one subduction angle to another, the slab needs to deform, and it can deform by stretching or tearing. Okay, so the other statement that I'd like to make is that some igneous strokes in convergent plate boundaries are spatially and geochemically anomalous relative to typical arc magmas. And I guess that we're all familiar with the kind of classic models, you know, the textbook models for arc magmatism. We get the hydration reaction from the subducting slabs at the overriding plate, the mantle wedge, partial melting in mantle wedge, and the kind of composition that we get are a typical calc alkaline series. Yet when we look at the examples, okay, it is. We look at examples from modern subduction systems, for example, we can see that there are many areas where we get anomalous geochemistries. And what exactly these anomalous compositions is part of the thing that we want to understand in the course of that project. But if we look here, for example, at the alkalinity, so just the total alkalinity, we can see that there are areas where we get arc-related or magmatism in the proximity of the subduction zone with a very high alkalinity. So shosonites or a high alkaline, other types of high alkaline basalts. So Mount Etna is an example of that. As I mentioned before, it's a volcano that has a kind of anomalous composition. It's you can see here in this example from a paper in Nature, showing that the composition of Mount Etna is some sort of mix of a normal arc magmatism and something that looks more like an OIB. If we look at the position of Mount Etna, we can see that it is a position in the wrong, you know, not where we expect to see the magmatic arc. The volcanic arc is expected to be situated perhaps 100 to 200 kilometers above the slab. We can see that Mount Etna is situated here at the edge of the retreating slab. So it is a spatially and geochemically anomalous volcano. Again, it does not react. Okay, here it is. And another example another cartoon from a paper that's showing that the Mount Etna is possibly the result of tearing rather than the typical kind of arc. It is a subduction-related volcano, but it is not directly related to the actual arc. So the way that we can look at that in a very kind of simplified cartoon is that if we have a slab producing a typical arc magmatism, if this slab is subjected to tearing or at the slab edges or any kind of asthenospheric window, and some dynamics in the asthenospheric mantle can give rise to a S-jump, especially in geochemically anomalous volcanoes. Okay, so the question that we ask is where today we can identify such spatial anomalies. So Mount Etna is one example. Where else we can? I mean, other Mount Etnas are pretty straightforward question. Concentrating mainly on modern subduction systems. Do they correspond with areas of slab deformation? So can we actually, in the same way that been done in Mount Etna, can we see that the anomalous position of the volcano is also related to slab tearing or slab edges? And are the spatial anomalies also marked by geochemical anomalies? So for example, higher alkalinity, enrichment in incompatible elements, perhaps a dacitic signature, all sort of different signatures, geochemical signatures that may tell us something about the geochemical anomalous magnetism. So we look at the way we approach it is by looking at a slab model. So basically, looking at the global slab model from Haynes and others. They published slab 1 model in 2012, and a couple of years ago they published the second version, slab 2. And what they basically did is creating continuous slabs in modern subduction zones by extrapolating earthquake, slab-related earthquake data. And we're using that as the general kind of approximation for the slabs, and asking ourselves specifically for example, in the example that I'll show in the Andes, in the northern Andes, is the slab model, how accurate the slab model is, and whether the slab is actually continuous in that part of the world. So I'll start the discussion about South America first. So as I said, we use here the slab models from the slab 2 models, and what we see here are the slab contours. And the other thing that we use is quaternary volcanism. So taking the database from the Global Volcanism Program and assuming that those are the volcanoes that, looking at all the volcanoes in the proximity of subduction zones, up to, so for the sake of this exercise, we took every volcano that is less than 250 kilometers from any of the slab contours. And those are the volcanoes that we want to kind of test are, how they are related to the subduction processes. Many of them are obviously the typical arcs, but what are where the deviations are. So these are the volcanoes, and if we look here, just plotting the information from South America, we can see a number of interesting observations. So first of all, we can see that the volcanoes in South America appear in clusters. There is a cluster here in the southern Andes, the central Andes, the northern Andes, perhaps even 2 different clusters with the gaps in between in the northern Andes, and the big gaps in Peru and Chile. This is, of course, no news. It's been discussed a lot in the literature, why those gaps are there, and I'll get to that a little bit later. Again, The other thing that we recognize is that there are volcanoes that at least assume, according to the slab model, they are not directly related to the slab. Yeah, so again, assuming that the slab model is correct, we do have volcanoes like Cerro Hudson or El Valle in Panama that are basically, they occur beyond the protection of the slab. They are not underlain by a subducting slab. And the third observation is that we have volcanoes that are anomalously deep. So volcanoes that the slab below is anomalously deep. So we expect that the process of a normal kind of a subduction factory would occur, would be generated at depth of say 50 or 70 kilometers up to 150 or maybe 200 kilometers. But there are a number of volcanoes that, according to the slab model, the depth of the slab is much deeper than that. So that is the third observation, and that basically can tell us a couple of things, and both of them are interesting. The first one is that maybe those volcanoes, like Cerro Hudson or the one here in Argentina, maybe those volcanoes are generated by a somewhat different mechanism. Maybe it's not only the typical arc, the typical kind of subduction factory, but maybe there's another component here that gives rise to a magmatism. The other possibility is that the slab model is inaccurate. So in fact, the slab does continue here, and there is an underlying slab below this volcano. And as I say, both scenarios are possible, and both of them are interesting if we can get more insight into them. So just getting back to the actual volcanic gaps here, we know that those gaps were generated by anomalies at the subducting oceanic lithosphere. Here we have the Nazca Ridge, the Iquique Ridge, the Juan Fernandez Ridge. Particularly the Nazca Ridge and the Juan Fernandez Ridge have a long history of subduction, and they were kind of sweeping the coast of South America and kind of disturbing the subduction dynamics, changing the angle of the subducting slab and destroying the subduction factory. So we think that we understand why the gaps are there. We can see that they might be related also. They seem to correlate to the occurrence of young giant ore deposits. And as I say, I might get back to that at the end of my presentation. But the interesting thing is that when we look at the Carnegie Ridge here, offshore Ecuador, we can see that it does not seem to correspond to, well, it does not correspond to a gap in volcanism. So some people suggested that there is a flat slab segment opposite the Carnegie Ridge. This is what I put here in the illustration in that paper from 2005. But and that is the kind of thing that we want to test again. So the Peru flat slab, we know that it is definitely there. They are very well constrained. You know, it is a cross section showing that the slab is flattening at a depth of about 100 or 120 kilometers. Same with the Juan Fernandez Ridge. And the question is, what is going on with the Carnegie Ridge subduction? So some people suggested that there is a flat slab segment in the just exactly a very narrow flat segment opposite the Carnegie Ridge subduction, and that is bounded by a couple of tears. Other models suggested, you know, we do have some slab deformation, but it's continuous and it's forming a kind of a curvature, so a bending of the slab, and that's the kind of thing that we decided to look in more detail. So what we basically did is taking the slab 2 model and testing it against seismic observations. The submodel is based on seismic observations, but as I mentioned before, it is an extrapolation of the earthquakes to create a continuous slab. And what we basically did is testing the consistency between observations and models. We concentrate on the northern Andes, so the transition from the Peru flat sub-segment to the subduction just offshore the Carnegie Ridge in Ecuador. We can see that if we look at the contours of the slab 2 model, we can very clearly see this transition by the curvature of the contours. So that is where the transition from supposedly a flat slab to a normal subduction occurs. Another thing that we can see here are the active volcanoes. One of the volcanoes indicated here in red, and that is the one that we concentrated in particular with regards to the geochemical data from that volcano. Okay, so that's the area. Here is a Google Earth image showing the northern Andean volcanic belt. So immediately north of the volcanic gap, we have a pretty broad volcanic belt, and it's made of front arc volcanoes forming those huge peaks of the northern Andes, and in a main arc here, a little bit at the more inland, and then we have a couple of volcanoes. So these are the Holocene volcanoes. In the following slides, I will add also Pleistocene ones. But when we look at the Holocene volcanoes, we see that we have a couple of volcanoes that are in the Black Arc region, El Reventador and the Sumaco. And Sumaco is the one that we were particularly interested in. As I said, I will show you the geochemical data very soon. We had the advantage of getting data from Sumaco volcano from our collaborator in California, Jennifer Garrison. She was able to get samples from Sumaco by helicopter support some time ago. It's very difficult to get there. It is very far from the trench, as you can see. You know, a long way in the back arc, and it's basically already surrounded by the forest. It's sitting on already the Amazonian basin from a geological point of view. So kind of an odd position for an arc-related volcano. Okay, so here we see the same kind of picture, just zooming in, and as I mentioned before, we added also the Pleistocene volcanoes. So from a geodynamic point of view, we thought that Holocene and Pleistocene together gives us a good insight on as far as from a geodynamic point of view, it's they both correspond to present day geodynamics as far as we're concerned. So we have the northern Andean volcanic belt. We have Sumaco volcano here, and we see the contours of the slab 2 model. Again, this very, very sharp curvature in the slab contours, showing the transition from a flat slab, from the northern edge of the Peru flat slab. Now, looking at the geochemistry of the arc, we can see that if we take all the data from the arc front and the main arc volcanoes, we put that on a total silica versus total alkali versus silica diagram, we can see that what they give us is exactly what we expect in magmatic arcs. We get kind of a typical calc alkaline compositions, andesite, dacites. And if we add the El Reventador, so that's the one that is situated in the back arc, it's still, it's a little bit more alkaline, but it's still kind of in more or less typical position. It is more in the back arc, hence it has perhaps less degrees of melting, so a little bit more alkaline composition. And here we have a couple of Pleistocene volcanoes that are situated also in the back arc, and Sumaco volcano is the one that is completely old. So similar to Mount Etna, that has a kind of a completely different composition relative to all the other volcanoes in the proximity, all the other volcanoes in the arc. Sumaco volcano gives us a very, very primitive composition in general, so very low in silica, mafic, and even ultramafic compositions, very rich in alkalinity. So on that diagram, it is all this kind of field is the so-called phonolytic series. If we take only the potassium, and it would be the like shoshonitic series. So essentially, what we see there are shoshonites. So I'll get back to the geochemistry again soon, but first let's take a look at the slab model and actual observations to support or refute its correctness. So here we look at the slab model showing in contours, and those are the intermediate earthquakes that supposedly are slab related. So they define the slab, and we can see that the flat slab segment here is very well defined by seismicity. So there are lots of earthquakes that you can see here around 100 kilometer depth, exactly as expected. And if we look at the northern part, so where the northern Andean volcanic belt occurs, there is much less seismicity. So the area is for some reason the area is warmer. The area is less seismic, but still we have a few. So there are some that could help us to define some sort of slab, but they are much less. It's going to be much less robust than the flat slab. And one really interesting observation is that there is an area here just south of Sumaco volcano that is extremely seismic active. It has a big cluster of seismic events. These are, by the way, the earthquakes from the ISC EHD catalog, which are very well located. So that's the reason that we use them. It gives us less events, but they are we know that the location is accurate. And we see that those events here are particularly deep. So they go down to a depth of more than 200 kilometer, 250 kilometer. And this is what the so-called El Puyo seismic cluster. Immediately north of the El Puyo seismic cluster, we have a seismic gap. So all the area here around the Sumaco volcano is a seismic gap. And I mean, the definition of the seismic gap is a bit kind of vague because the area in general is not particularly seismically active here. But what is interesting is that there's a very sharp boundary between an area that is very seismic active and an area that has no seismicity at all. And this boundary is kind of a northeast southwest line. Another way of looking at the data is to look at the CMT, the focal plane solutions, and if we consider that the tension axis gives us some approximation of the stretching along the subducting slab, then we can get some interesting insight into that, particularly for the Peru flat slab, where we get we see that the t-axis, the tension axis, is east-west as expected, and the plunges or the dip of the slab would be very shallow, so a flat slab. If we look here in the north, again, not very well defined because we don't have so many events, but what is really interesting is that the El Puyo seismic clusters gives us, first of all, a kind of a consistent deviation in the orientation of the t-axis, so kind of a counterclockwise rotation of the t-axis, basically telling us that the movement, the direction of subduction becomes, rather than east-west, or rather than subducting to the east, we get subduction like a segment of the slab that is actually subducting to the northeast, and the plunges of the t-axis becoming much steeper. So essentially, a kind of a segment of the slab is kind of subducting at a higher angle. So that is really interesting. And we can look at the same kind of features in cross sections. And this is where, you know, even in an area that is not particularly seismic active in the northern Andes, we can still see that there is a picture here of the subducting slab. It's a we know that the slab is there because the arc is so active, and we see that there are, you know, sufficient kind of events in order to define a slab. The ones that we see here in we see the focal plane solutions as before in colors. We can see the circles, the big circles are the EHP data, and the small dots are all the rest of the ISC catalog that are less well located, but they still give us some constraints. And we can add that to we can look at the slab model in comparison to the observations. What we see here are the continuous line is the center of the cross section, is the cross section here. And it's obviously a composite cross section, taking the whole rectangle here. And the dashed lines are the two edges. And we can see that there's general kind of consistency between, you know, the slab, the slab that is interpreted from the observations and the slab 2 model that is shown here by these 3 lines. Okay, so this is that's the cross section in the northern Andes, showing, you know, kind of normal subduction, so 35 degrees subduction, and the generation of the arc shown by the triangles on top. If you look at the cross section, the composite cross sections here in the south, so that is the area of flat subduction. We see that it is very well defined. So we can beautifully see here the slab, the flattening at the 100 kilometer depth. That is the slab 2 model, and very good consistency between the slab 2 model and the observations. So that is the slab. And the interesting cross section is the one that runs from north to south. So it's a little bit counterintuitive because it's not the direction of subduction. So what we see here is the El Cuyo seismic cluster. Yeah, this is south, this is north, and we can see here that the cross section goes through the area of flat subduction here, 100 kilometer, and then in the El Cuyo seismic cluster, we see that we get a kind of part of the slab that starts to subduct, like as a northern component of subduction. Yeah, as we saw before with the tension axis. And as we get here, that would be this cross section that we see here on top. So kind of the slab, the normal slab in the northern Andean volcanic belt. That is a slab 2 model. The slab 2 model assumes continuity. Okay, that's the whole way that that it is built. So there's continuity from the normal subduction component here to the flat subduction here. And we can see that in this cross section, we see that the slab 2 model predictions are actually at odds with observations. There are a whole bunch of very well located seismic events in the Cuyo seismic clusters that are way deeper than what the slab model predicts. There are others here in the northern part of the Peru flat slab that are much shallower than the prediction. So we see that we get discrepancies between the slab 2 model and observation. So, you know, perhaps an interpretation like that would be more accurate interpretation to what we actually see in the observations. A slab 2, a slab that is that has some component of a kind of a northern subduction in the El Cuyo seismic cluster, then some gap, and then the normal subduction in the northern Andes. Another way of looking at the same thing is just to compare the seismic events, the depth of the seismic events to the slab 2 model. So the color code here basically telling us if the earthquakes is as predicted from the slab 2 model, or whether it's too deep in red or too shallow in blue. And we can see that here, for example, those neutral colors basically tell us that the model is consistent with observations. We get here to the northernmost part of the Peru flat slab, and we see that we get a whole band of earthquakes that are too high relative to the slab to a prediction. Then a seismic cluster is too deep. So we get, it's not like a random kind of discrepancy. It's a real kind of asymmetry that of earthquakes that are too shallow here, too deep here. Then we have the seismic gap, and particularly because of this kind of organized asymmetry, we think that it is actual. What we actually see is inaccuracy in the slab 2 model. The model is not continuous. The model is actually torn, and the tearing is likely to occur exactly where we transition from the seismic area to the seismic gap. So that's our interpretation for the slab tear that occurs just south of Sumaco volcano. And with this information in mind, we can go back to the geochemistry of Sumaco. So what we did, I'm not a geochemist, but we worked with John Caulfield, and what John did is basically modeling the geochemistry of Sumaco and the geochemistry of like a normal arc-related volcano, is try to see if we can reproduce them, using a normal subduction factory or something that is quite different. So first of all, if we look here, we can see that these are the different compositions that we get for Sumaco. We can choose the most primitive kind of version of Sumaco with 10% magnesium O, and we can compare that to a volcano from the same kind of latitude, the Casa volcano from the front arc, and we can see that consistently the compositions are different. So what John did is basically taking the kind of classic model for production of arc magnetism, so taking all sorts of different ingredients, 10% melting, that is kind of acceptable for arc magnetism, and just basically cooking something that will reproduce the composition of the arc, of the typical arc magmas. And it looks pretty good. Whether it's correct or not, I don't know, but it seems that we are able, with 10% melting and those ingredients, we can reproduce the magnetism in the composition of the arc front magmas. If we look here at a diagram of niobium yttrium to lanthanum ytterbium, we can see here kind of a line of melting, of the degree of melting. So 10 degrees of melting would give us, the kind of compositions that we get in the arc front and the main arc, and particularly when we add the kind of Rayleigh fractionation plots, we can kind of reproduce those, for climate parks and for appetite, we can reproduce those compositions, and it all the model seems to be a good one. If we look here at Sumaco, we need to have a different model to explain the compositions of Sumaco. So what John did here is taking a very, very low degree of melting, so less than 3% of melting, and a little bit of a complex kind of composition involving some metasematism from a slab melt as well. So the slab is the volcano is subduction related. It is related to a slab, to the slab processes, but it is not directly related to it is not a classic kind of mechanism of arc magnetism. And again, if we take 3 degrees here and the fractionation, we can see that we can reproduce the Sumaco volcanoes, and similarly with the rare earth elements, we can reproduce them pretty well. So in conclusion, Sumaco is not generated by typical arc processes. It is positioned above an inferred tear, so that is the kind of 3D model that we have in mind. A very modest tear, very small one. Its continuation is kind of parallel to the Grijalva fracture zone. So maybe it is the existence of the fracture zone showing basically transition from two different lithosphere, different ages of lithosphere. This is where the tearing, where there would be preference for tearing to occur. And perhaps the reason that we get Sumaco volcano where it is because of a kind of a trapdoor mechanism. So kind of during the formation of the flat slab needs to evolve in one way or other. So if that was, if you remember the north-south cross-section that we had, and if we look at this cross-section schematically through time, we need to kind of, we develop the flat slab and gradually stretching and bending the slab. This is the Grijalva fracture zone. And as this process continues, at a certain point, the whole thing will snap and producing a kind of a trapdoor mechanism that can also allow, perhaps allow some sort of a colloidal mantle flow that will actually generate the melt, generate the heat that is required for the melt, so heat by advection. So how am I doing with time? Can I continue or do I need to drop out?
I think so. I think there is some thoughts that lunch will be delivered, but no signs of it.
So well, you stop me if I go too long. I don't have a. Okay, yeah, that should be fine. So you know, just looking at the larger picture again, the Hollandian system. So that is the Grijalva tear, where we just saw the example of Sumaco volcano, and there are a whole bunch of other tears that have been suggested in the literature. So, for example, in Colombia, we can see here, you know, kind of a displacement in the way that the slab behaves. There are tears that have been suggested in association with the Nazca and Juan Fernandez bridges, and another one here in Patagonia, again related to a fracture zone, the Mocha fracture zone, and we can see here in the seismic tomography that again we see some sort of displacement. So you know, possible tears. And one of the things that we started entertaining with is how whether those potential tears or whether the anomalies, the spatial anomalies, are also associated with geochemical anomalies. So the first thing that we did is computed the depth of the slab beneath each volcano using the slab 2 model. And that's what we see for South America. So the three clusters here, the Juan Fernandez and Nazca kind of tears are areas of volcanic gaps anyway. So there's not really any potential for geochemical anomalies there. But if you look at the Mocha, for example, and the Grijalva, so that would be Sumaco, we can see that if you look, for example, at total alkali, there is, you know, a kind of a spike in total alkali in that this is just done based on latitude. So this is where I start with kind of a immature material. So the diagrams are going to be a little bit coarse. We took all the data from GeoRock, and we see that you know, perhaps it is the tears that also the tear-related volcanoes that also have some geochemical characteristics. Yeah, we just played with different parameters. Don't know exactly what they mean, but you know, one thing that one thing that we recognize here, for example, is that there's a general kind of increase from south to north when we look at strontium terbium or strontium yttrium. So perhaps, you know, increasing involvement of slab melt. You know, I looked at where the real adikites are, so just filtering the data. But I don't really know how it is related to those potential tears. That's basically what I mean. And one of the things that we want to explore. You know, just moving to different areas. You can see here in the Isu-Bonin Mariana, the tears that Louis already mentioned briefly. And we can see that if we look at the volcanoes here, just color codes, we can see that we get volcanoes that the slab is seemingly deeper compared to those to the normal kind of art. Again, this is the slab depth versus latitude. And at least in the example here, you can see, so this one is for Ogasawa there, you can see that there are kind of geochemically, there are spatially anomalous volcanoes, so the slab is somewhat deeper. And again, we look at the alkalinity, we see that they are particularly more alkaline. This is a Kural, and just a slab depth. Here there are, the slab strike obviously showing a major change around here. And one interesting spike here with the sodium. Sodium perhaps, rather than looking at total alkali, if you look at sodium, it gives us maybe insight more on mantle processes. So, perhaps, something is going on here. What else? Yeah, just the different parameters. You look at Indonesia, we see a really interesting pattern. That is again the slab depth versus longitude, and there's really there's a pattern here. This kind of shallowing of the depth of the slab beneath the volcanoes in each segment, and then kind of a major an abrupt change. And this change occurs, in the proximity more or less of those anomalous volcanoes, Muya and Lassem. They are, I don't know if you're able to see them, they're at the very top of the diagram. So there are volcanoes that the slab, according to the slab model, is way too deep. So again, maybe another example of what we saw in the Northern Andes, that the slab model is actually inaccurate and is, some sort of tearing in fact could occur here and perhaps also around here. And perhaps here, where we know that the slab is not continuous here. There's no real active subduction beneath Timor. And so that's one area that we know that the slab approximation is incorrect. And again, we get a volcano here, Batutara, just at the edge of the seismic gap. And Batutara and Muya are the ones that gives us also the geochemical anomalies. So again, this is just look at the total alkalinity. This is a lanthanum to terbium. Muya gives us a very large kind of spike. And the last thing that I just kind of, I thought that is curious is this kind, so again, these are just slab depth versus latitude or longitude. And one kind of curious shape that we keep seeing in many of those diagrams is this kind of deepening of so the slab is deeper at the center of each volcanic, each segment of the arc. So, this is the Kural, for example, and we see that, it is like we get segments of arc magmatism, and it is the central part of the segment where we get a larger width of magmatism and magmatism also that is supposedly underlain by slab that is much deeper. So, maybe, that's not necessarily related to like tearing or, S-jam or anything like that. It tells us maybe something about the kind of maturity of the system. The system is most mature at the center of each slab segment. So, just entertained with this kind of diagrams. Some of them are more data rich now. We see the same in South America. And so, quite large anomalies in South America when we think, most of the arc is around 120 kilometers as expected. And at the center of each segment, we get volcanoes that are also underlain by deeper slabs. And and the last, last few words about linked to ore deposits. We think that it could be directly linked to the occurrence of a large porphyry and epithermal deposits. And that's something that has been suggested quite a lot. This is an example from Garwin, basically arguing that the localized asthenospheric upwelling in response to tearing might play a crucial role in ore formation. So we need to have this contribution of asthenospheric material, that will bring the metal, will enrich the system. And perhaps, this is from the reconstruction that we did a while ago of the subduction of the Nazca Ridge. Perhaps the link that we see between ore deposits and the subduction of the Nazca Ridge is related to S-jam magnetism. We don't find it in the diagram that I showed you today because they show the present day volcanism. But perhaps magnetism at around 15 or 14 million years ago was in fact S-jam magnetism related to tearing that occurs here at the time of the subduction. Again, exactly the kind of things that Louis has shown in his models. Okay, we can see that there is a clear link between the subduction and the ore deposit, and perhaps S-jam plays a major role. The other thing is that if we look at the big deposits, we see that many of them occur in high alkaline rocks, shoshonites, for example. The proportion of ore deposits associated with shoshonites is much larger than the occurrence of shoshonites in general in arcs. So again, perhaps it is the S-jam, perhaps this high alkalinity that is really important in the actual formation of ore deposits. So I will finish with that. The ability to recognize S-jam in the geological record might provide information on the preferred position of ore deposits within arc systems. So if we are able to kind of tell what actually are the geochemical signatures of S-jam, not in the way that I did, which is still kind of rudimentary, but in a more kind of really recognized patterns, then we'll be able to go to the geological past and ask ourselves, do this sequence of rocks actually meet this pattern? And if yes, maybe they could lead us to a ore deposit. Some, but maybe not all, S-jam volcanoes seem to correspond to mantle flow in response to slab tearing and slab edges. And the exact geochemical signature of S-jam is yet to be determined. Could be, the high alkalinity, or enrichment in incompatible elements. I don't know, kind of adiabatic signature or anything else. And that's all. Thanks.
So lunch is waiting, but we should ask you some questions in advance, particularly the people who won't get a full chair for lunch. So let's concentrate on questions from the remote people, if they can hear me.
Any questions from the remote people?
Right, questions from the hungry people.
I am working on some geochemical data of arcs as well, related to the porphyry deposits. So I have a question about the rare earth element pattern that you showed. There is quite a big European anomaly, which is normally related to the plagioclase, which means the magma was very dry, because the negative anomaly would be created by amphibole, right? So how is it related to the archimagmatism and prospection of some new deposits? At the moment, we think that, well, a general idea of creating some porphyry deposits, the magma should be wet, and it should be, well, calc-alkaline, high calc-alkaline or shoshonitic, right? So how is it related? Do you think that it has some potential to create some porphyry deposits or not really?
I don't know. With the European anomaly, I can't really answer your question.
That's okay. So, okay.
Yeah, I don't know.
So my other question is, because it seems to be consistent that the geochemical data kind of varies with the distance and the distance from the slab as well. So do you think, because it seems from your data that the most high calc-alkaline magmas are further from the slab, do you think there is some prospection over there, that the deeper it is, the more prospective it is?
Well, I think that the distance from the distance is representing also the degrees of melting.
Yes.
So, I mean, it's not a surprise that when you go further from the arc, from the trench, you would get more and more high alkalinity. So, you know, whether high alkalinity alone is a recipe for all deposits,
No,
I
probably
don't know.
not.
Yeah, probably not. Maybe it is like we saw with Sumaco. You know, we compared Sumaco to El Reventador, that was more or less the same distance from the trench. El Reventador seems to, I mean, it's a little bit enriched in potassium and sodium, but it does not give us the whole suite of kind of you know, enrichment in incompatible elements. And according to our kind of model, it is produced in a normal kind of subduction factory, further from the arc, therefore, you know, low degree of melting. Sumaco has a contribution from, you know, perhaps some asthenospheric source, you know, this,
Yeah.
it has this kind of local colloidal, you know, mantle flow that generates, you know, a little hotspot, and perhaps for, you know, for the enrichment in metals, that's what you need to bring, you know, some additional material from, you know, from the asthenosphere, for example.
Okay. Yeah, quick one from Rodri, and then we need to break for lunch.
So the mechanism you proposed for the kind of colloidal flow around the base of the slab, it kind of potentially works in terms of geochemistry. Do you see any evidence for dynamic topography or uplift at the time in the geological record that supports that flow?
Can you repeat that question?
Well, the question is if we see any evidence for dynamic topography for like our suggested colloidal flow. That's the question,
Yes,
right?
Yeah.
I don't think so. I mean, we didn't check it specifically for the area of Sumaco volcano, but you know, I'm not aware of any major anomaly in
I
the
think the
area.
whole region would be going down, so I think it would be quite hard potentially to try and identify maybe a temporal change that supports that mechanism.
Yeah, I mean, it's something that did cross our mind in general, that you know, these kind of processes should should give us you know, you look at the, you know, northern Colombia, for example, you find like I don't know, 3,700 meter elevation, very close to the Caribbean, and you think, you know, something is going on there, you know, with the edge. That is exactly where you have the edge of the slab, and you have a huge mountain. So, you know, maybe these are the kind of areas that they've been affected by, you know, by that kind of mantle flow. We don't get volcanism related to that. But yeah, specifically for Sumaco, we haven't seen that.